Once again, assuming my role as a disembodied voice, we are going to finish section 12 today, the section on alternating currents. And just to briefly summarize where I'd left off, we're looking at resistors, inductors, and capacitors. How do they behave as an alternating current passes through them? Well, each opposes the flow of current in its own particular way, okay? A resistor, well, it resists. As the electron, let's say it's a metal. In other materials, the flowing particles might be something else, but in the case of a metal anyhow, it's electrons trying to push their way through the metal. Well, the surrounding material gets in the way as they try to flow, and that's the basic nature of electrical resistance. Electrical resistance takes energy away from, oh, wait a minute, I gotta do something with the focus again here. It's throbbing. Just slightly changing the angle that the camera is hanging at seems to have an effect on that. Anyhow, resistance is from the electrons experiencing interference from the surrounding material, and it takes energy away from those flowing electrons and converts it into heat, where it dissipates into the environment. Capacitors and inductors, I'd actually gotten through inductors in the previous recording. The next thing was supposed to be capacitors, but I wasn't going to go through that in detail again as a just to save a little time. I was going to say, well, you know, it was kind of sort of a little bit like what I said about this up here, and here's the results. So just to kind of summarize, capacitors and inductors both oppose the flow of current in a way that's called reactance rather than resistance. Inductors, it's a magnetic effect. Capacitors, it's an electric effect. Okay, you're dealing with a magnetic field here. You're dealing with an electric field here. In the case of an inductor, it's the self-induced voltage that pushes back. Or if you want to look at it at a more fundamental level, it's the changing magnetic field induces an electric field that pushes against the flowing current. Whereas here, it's a static electric field between the plates of the capacitor that pushes back against the current during that part of the cycle where something to point with, during that part of the cycle where the current is building up. And of course, once you've gotten this far, you've established the amplitude. It just flows on from there. But during the part of the cycle where the current is building up, the charge already in the capacitor pushes back against additional charge trying to flow in, and because like charges repel. So resistor, it's the surrounding material getting in the way. In an inductor, it's the self-induced voltage getting in the way. And in a capacitor, it's the charge already in the capacitor getting in the way, pushing back against the additional charge that's thinking about trying to flow in. So very similar to inductors, you have voltage equals the current times a form of reactance, this time called capacitive reactance, which is equal to 1 over omega times C. Notice that this is the opposite of an inductor. Okay, if you flip back into your notes a little bit, inductive reactance was omega times L, whereas here, omega and C are down in the denominator, so this time it's an inverse proportion. Low frequencies go through a coil really well. The lowest frequency of all is 0, which would be direct current. And as I've said before, to DC, a coil is just another wire. So low frequencies slip right through it, but high frequencies have the current changing extremely rapidly, and the self-induced voltage depends on the rate of change, so you get a big self-induced voltage pushing back, and high frequencies don't like to go through a coil. Capacitors, it's the other way around. For a low frequency, well, I've probably said this before too, to direct current, a capacitor is a broken wire. You don't have a complete circuit because you don't have a connection between the one plate and the other. High frequencies, on the other hand, there is so little time for the capacitor to charge. You know, like if you've got 1,000,000 cycles per second, a few electrons flow into the negative plate, and before they even have a chance to unpack their suitcases, it's time to turn around and go back. Okay, so, and then shortly after that, it's time for them to flow back in again. So if you have, yeah, there is the source of alternating EMF. That symbol is to an AC circuit what a battery symbol is to a DC circuit. And if you have a capacitor, well, the electrons flow in, the electrons go back, the electrons go in, the electrons go. You don't need a complete circuit. It doesn't matter that this thing is kind of like a broken wire. The electrons just jiggle back and forth anyhow. You don't really need a complete path all the way from one side of the EMF source to the other. The higher the frequency, now let me back up. The thing, once again, that opposes the flow of charge into this capacitor is the charge that's already in it. And the higher the frequency, the less time there is for that charge to accumulate. So the lower the average charge, the smaller the opposition, and that's why the number of ohms is inversely proportional to the frequency. So coils and capacitors are filters in a sense. Low frequencies go through a coil, but they filter out high frequencies. High frequencies will go through a capacitor, but they filter out low frequencies. And the capacitance, of course, is also a factor. There is more room for charge in a higher capacitance capacitor, so more capacitance, fewer ohms. So I've already said that. I've already said that in considerably more long-winded way than the way I've got it written there. So there's the relationship that will play the role of Ohm's law. Volts equals amps times ohms. As for the phase angle, well, the quickest way I could think of to explain it was just to apply the loop rule. If you've got an LC circuit, and actually when I did LC circuits near the end of the previous section, I ran through all the math and pointed it out. Well, I didn't completely point all of this out, I guess, but if you apply the loop rule to this, it says that at any time, because the loop rule would apply to the instantaneous voltages, at any instant you care to consider, the voltage across the capacitor has to be the negative of the voltage across the inductor. So, do I still have the sketch down here from last time? Yeah. Notes from last time. If the voltage across the inductor is a cosine, then based on this, the voltage across the capacitor would have to be a negative cosine, one that starts in a trough instead of at a peak. So if voltage leads in a coil, the voltage lags in a capacitor, meaning that whatever happens, the current does it first and the voltage does it later. The current starts out going up through 0. Quarter of a cycle later, the voltage goes up through 0. Current does it first, voltage does it later. So in a resistor, they're in phase. In a capacitor or an inductor, there's a 90-degree phase difference. That much, I think, is pretty easy to remember. The tricky part is remembering what's supposed to lead and what's supposed to lag. And for that, remember Eli the Iceman. It's one of those make-believe people. He lives just down the street from Roy G. Biv. E as in EMF, E for voltage, L for inductor, I for current, C for capacitor. So in an inductor, well, E is on the front of the word, so voltage leads. I is on the end of the word, so current lags. Inductor, voltage leads, current lags. In a capacitor, current leads, because it's on the beginning of the word, and the voltage lags. And just to go off on a brief tangent for anybody who doesn't know what an Iceman is, once upon a time, people did not have refrigerators. What they did is in the wintertime, a bunch of guys with great big saws and a big sled that was pulled by these, these big draft horses, they'd go out on the rivers and lakes when everything was frozen, just the dead of winter, and they'd cut blocks of ice and they'd load them up and haul them back into town where they had a big warehouse, and they'd pile up all this ice. And when they were done, they'd throw about 4 feet of straw on top of it. And this would, it's called an ice house. And this, they'd take all summer for the ice to melt. Okay. And in fact, they'd even load some of it on trains and send it into the South and sell it to people down there. It's, well, as often happens with technological advancement, when refrigerators became common, a whole type of livelihood got exterminated. But anyhow, you'd be living there in your house or apartment, and instead of a refrigerator, you had an ice box. People still use the same technology today. Sometimes when they go camping, you've got the cooler, and every day you have to go over to the camp store and buy a bag of ice, and you throw it in there, and that keeps your perishable food from perishing. But anyhow, the Iceman is the guy who came around every few days and sold you another block of ice. Delivered it. Time to do a problem. We have here ordinary household alternating current, 60 hertz, 120 volts. And let's say, and this would be one of those don't try this at home, kids, kind of things. Your mother may have mentioned to you when you were 3 years old that it's a bad idea to stick metal objects into an electrical outlet. But if, someone wearing appropriate protective gear, rubber gloves or something like that, was to do this, how many amps would flow through this capacitor? That's the question. So get that out of the way and maybe throw it there. And so actually this little picture is exactly what's going on in this question. 12.2. So it's basically a two-step kind of thing. The question asks how many amps, that's I. And it tells us how many volts, 120 is given in the question. So I have to figure out how many ohms. So step 1, do this to figure out how many ohms, put it in that. Step 2, solve for I. So that is the plan of attack. XC, capacitive reactance, 1 over omega C. omega is 2 pi f, so 2 pi times 60 hertz. When you've done this enough times, you remember that that's, I think it's 377 radians per second. Yeah, that's right. Convert microfarads to farads. 6 times 10 to the negative 6. And that comes out 442 ohms. Amps equals volts divided by ohms. .271 of an ampere. And then I guess it's on the next page. But the third question just says repeat. What if the frequency had been 600 hertz instead of 60? Well, the reason this is here is just to illustrate an important difference between resistance and reactance. Resistance is a fixed property of the resistor. Okay, and unless you do something like overheat it, we saw in one of the labs a while ago that resistance changes with temperature. But unless you overheat the resistor, a 442 ohm resistor is a 442 ohm resistor, end of story. A resistor doesn't care if the frequency is 1 hertz or 1,000,000 hertz. The surrounding material gets in the way of the flowing electrons to the same extent. Either kind of reactance, XL or XC, on the other hand, is a function of the frequency. So if you have some way to turn up the frequency, I'm not even going to bother to write all of this out again. I just got a different color pen here. And I'm just going to put another 0 there on the frequency, which means the decimal point gets moved over to there, which means the decimal point gets moved over to there. So it's almost the same problem all over again. It's just that now XC is 44.2 ohms, which implies that I is 2.71 amps. So that's what happens if you put a capacitor or an inductor or a resistor, you hook it up to a source of alternating voltage. What if you hook all three up to a source of alternating voltage? Well, the only case I'm going to take time to look at is a series circuit like this. I guess I should start about there. The source of voltage is somewhere beyond the edges of the picture, but we've got R, L, and C in series with each other. A parallel circuit is a variation on the same story. Just to briefly summarize something I'm not going to expect you to know. In a series circuit, the current has to be the same everywhere, okay? At any given instant, the rate that electrons are flowing through this wire has to be equal to the rate of the electrons flowing through that wire. It equals it there, because where else would the electrons go? It's like if you got water flowing through a hose, at any point along the hose, the number of gallons per minute, it's the same all the way along, okay? Because of the phase differences, the Eli the Iceman thing that I was talking about, there'll be phase differences between the voltages. If you measure the voltage between here and here like this, or if you measure the voltage across the inductor like that, or if you measure the voltage across the resistor like that, those voltages will have these different phase relationships like I've sketched here. In a parallel circuit, it's the other way around. When things are connected in parallel, the voltage is the same across each of them. So in a parallel circuit, you'd have the same curve for the voltage on all three of them, and the currents would lead or lag. Okay, at one instant, the current's going through the coil. Short time later, the current is going through, in a parallel circuit, going through the capacitor instead. And meanwhile, it's always the same amount going through the resistor. And so anyhow, a parallel circuit is a variation on the same story, but we'll just look at a series circuit as the only one we have time for to go into in depth. So everywhere in the circuit, this is the current. In a resistor, the voltage is in phase with the current. So when the current peaks, the voltage, well, this voltage here, the voltage between that point and that point, when the current peaks, the voltage peaks. When the current goes through zero, the voltage goes through zero, and so on. ICE, current leads, voltage lags. The current starts out going up through zero, quarter cycle later, the voltage goes up through zero. Here, ELI, the voltage leads. The voltage starts out at a peak, quarter of a cycle later, the current is at a peak. Voltage leads, current lags. Why does this matter? Because it has a great effect on everything that's going on in the circuit, basically. Let's say, well, let's bring the resistor into it in a moment. For a simpler case to look at for a warm-up, let's say you had just an LC circuit without any significant resistance, and you measure the total across both things, and you want to compare that to the voltage measured across each individual item. If this was a DC circuit, what numbers did I use? 5 and 4. Okay, we'll stick with the way I wrote it. If this was DC voltages, then if this meter said 5 volts and this was a meter that said 4 volts, then this meter would say 9 volts. But with AC voltages, not so fast. Okay, if this says 5 volts and this says 4 volts, this one says 1 volt. Because if you look back up here at the graphs, anytime the voltage on the inductor is positive, the voltage on the capacitor is negative. And anytime this one is negative, that one's positive. So when you add this function plus that function, they cancel each other out rather than reinforcing. And so 5 and 4 gives you 1. Now, let's generalize and include the resistance. The voltage across the resistor is not quite in phase with either one of these, and it's not quite out of phase with either one of these. Rather, it's kind of halfway in between. So you get something more than subtraction, but less than addition when you throw this in. And, well, I wrote out what happens down here because I didn't want to take the time in class. There's something I just wanted to summarize. The instantaneous voltages, the DC voltages, add up. So the total across the whole group is voltage across the resistor, voltage across the capacitor. You add them all up. The voltage across the resistor, like it shows in the picture, the voltage across the resistor is a sine. The voltage across the capacitor is a negative cosine, and the voltage across the inductor is a positive cosine. Well, if you want to take an algebraic approach to this, what happens next is, you know, an algebraic, a lot of algebra. You make some clever substitutions using some trig identities, and if you want to have RMS, root mean squared, instead of the peak values, you would, well, I think things get squared at some point as you're going along, and then you divide by 2. But if it's just the voltages you're talking about, it would be the square root of 2, actually. When the smoke clears, the relationship between, well, here I called it T for total. I just called it just plain delta V without a subscript here. But this, if you had nothing else in the circuit besides these 3 things, and the ends of the wires here and here were plugged into an outlet, well, this would be the voltage of the outlet. If you stuck it in a 120 volt outlet, delta V would be the 120 volts. And each of these would be what the 3 meters on the individual things read, okay? Now, you may notice this bears a striking resemblance to the Pythagorean theorem. That formula that comes from the, if you want to try and derive it algebraically anyhow, it comes from the procedure I was just describing. That behaves like you're doing vector addition. Like you've got that, that, and the total voltage across the whole group is the resultant, the hypotenuse. Also, the phase angle for the entire group. If you have an oscilloscope or some measuring device like that, a computer with a voltage sensor that acts like an oscilloscope, if you measure the voltage between here and here across the whole group, how far out of step is it compared to the current? Well, if you had a purely resistive circuit, nothing but resistors, they would be in phase with each other. The phase angle would be 0. If you had a purely inductive circuit, nothing but coils, this phase angle would be plus 90 degrees. If you had nothing but capacitors in there, then the phase angle would be negative 90 degrees. But with sum of all 3, the amount that the current and the voltage are out of step with each other could be anywhere between those extremes, anywhere from negative 90 to plus 90, okay? And that amount of phase difference would be equal to this angle that I drew here. So phi is the phase angle for the circuit as a whole. Phase angle for the circuit as a whole. Now, voltage, I should probably emphasize this, potential voltage is a scalar. Okay, voltage does not have a direction like, 12 volts to the right or 4 volts upward or something like that. These are not real vectors that exist here in the real world where we live. Rather, these are what are called phasors. This is a phasor diagram. A phasor is a vector in phase space rather than in, rather than the real world where you and I live, phase space being sort of a mathematical abstraction. With an actual vector, like a velocity vector or an electric field vector or a momentum vector or anything like that, the direction represents which way does it point through the world? Does it point toward the east? Does it point toward the north? Or does it point horizontally or vertically? Here, the phase angle, or here this angle, the direction of the phasor, represents the phase of a vibration rather than an actual direction like north or east or something like that. Okay, so the direction you draw the arrows represents the phase of the vibration rather than an actual direction, a vector in phase space. I guess the short version of the story is just to call this a picture that's suggested by the formula. So next thing it says on the script here is impedance. If you take that formula and divide through by the current, you'd have delta V over I on the one side of the equals. Now, if you have, 1 over I times the square root, when you take I inside the square root, there's a bunch of other stuff in there I don't feel like writing down. That would be equal to the square root of 1 over I squared times all that other stuff. Square root of I squared would be I. So once I get it inside the square root, I'm going to distribute it across all of these terms here. I'm going to use the distributive property, and you'd have delta VL over I minus delta V on the capacitor over I. Well, that, the voltage across the resistor divided by the current, that's Ohm's law, R equals V over I. Likewise, for the inductor, the volts divided by the amps is how many ohms you've got from the inductor, and how many volts divided by the amps for the capacitor is how many ohms you've got for the capacitor. Delta V over I for the circuit as a whole, well, that's, this is going to be the number of ohms for the entire group, the effective number of ohms for the group taken as a whole, and that is called the circuit's impedance. represented by the letter Z, square root of R squared plus XL minus XC squared measured in ohms so substituting that into here, well, plus multiplying both sides by I, the volts across the circuit as a whole equals the amps times the number of ohms in the circuit as a whole. I find people fairly frequently want to get the impedance mixed up with the resistance. I'll have a problem where there's a group like this, and I'll tell you this, I'll tell you C, I'll tell you L, I'll give you R, give you numbers for all those things, and I'll tell you it's hooked up to, I don't know, 50 volts or whatever. How many amps flows? And people think, oh, Ohm's law, V equals I times R, and the I times R gives you how many volts between there and there. I times R is the voltage across the resistor. The voltage across the whole group corresponds to the number of ohms for the whole group, and that's the impedance. Resistance is just for the resistor. Okay. So you look at this, looks like the square, or it looks like the Pythagorean theorem again, and so there'd be another one of these phasor diagrams. I think I've got both of them on the formula sheet if I remember right, but this time the same phase angle down here, same one that we had over here, because all you're doing is taking this triangle and dividing the length of each side by I. So you're going to have similar triangles. XL minus XC on this side, the resistance on this side, and the impedance is the hypotenuse. So resistance and reactance are kinds of impedance. Overall, how much the circuit impedes the flow of electricity in any way is the impedance. Time for an example. We have a capacitor, we have a resistor. Once again, standard household electricity for North America. Europe is a higher voltage. It's like 220 volts or something like that. They use a different frequency also. They're 50 hertz over there instead of 60, as I understand it. So, well, maybe I should summarize the strategy before I write out the details. Find the current. Well, it's kind of like in number 2 and 3. It said find the current. The first thing I had to do was figure out how many ohms there were. And that'll be this thing here. Okay. Of course, before I can do that, I have to figure out XL and XC. Resistance is given. So start out by determining the reactances, drop them in, then you've got Z, which is how many ohms the entire circuit has. And then once you have that, you get the current out of, I can't quite see what I'm pointing at. Once you've got that, you get the current out of this. Amps equals volts divided by ohms. So that's the summary. That's how I plan to go after this. Capacitive reactance. kind of similar to that other one I did. 2 pi f is the angular frequency. And this time the capacitance is 5 times 10 to the negative 6 of a farad. 5 microfarads. So if you manage to push the right buttons, you have 530 ohms from the capacitor. As for the inductor, now this I've found kind of throws people sometimes when I give them something like this. They go, I don't have any number to put in for L. You know, XL equals omega times L. If there is no inductor, then the current is not being impeded by an inductor in any way. The inductor that's not there does nothing to oppose the flow of current. Impedance R squared. R is 300 ohms. XL minus XC. So altogether, we've got 609 ohms in that group. And finally, to get the current, I equals the voltage across the whole group divided by the ohms for the whole group. Again, you need the impedance, not the resistance. Having said that 4 or 5 times, I am still pretty confident that if this sort of thing comes up on a test, somebody will do that. $197 milliamps. When you get to lab number 12, you need to do a similar type of calculation, except XL will not be 0. You'll have an inductor to include in all of this. Then once you know the current, there's a few more steps. You're supposed to calculate for the lab. You're supposed to calculate the voltage for the resistor, the inductor, and the capacitor. Well, voltage across the resistor is IR. Voltage across the capacitor is I times XC. For the coil, it's I times XL. Okay, once you know the current, this is the current through everything in a series circuit. And multiply it by the number of ohms each individual thing has, and that'll tell you the voltage across each individual thing. And then you compare what's calculated in that way to what actually gets measured with an oscilloscope. Top of the next page says power, wattage, as some people like to call it. Now, back at the beginning of this unit, root mean squared voltage and current were deliberately defined in order to make average power equal to I squared times R. Or if you're calculating it from voltage, it's equal to V squared over R. Okay? But that would be the voltage across the resistor. Let's stick with this. So I squared times R. Well, you know, let's say the resistance is not something you have right at your fingertips. We saw back in the section on DC that power could be found from I times V. That needs a little modification when you're talking about an alternating current, okay? Power is equal to I squared times R. had that in mind when we defined root mean squared current in the first place? Well, the resistance is equal to, well, let's take it a step at a time. I squared, I divided it up into I times I. So I squared times R, average power. I times R is equal to the voltage across the resistor. That's Ohm's law. But, you know, if you've got something like the last problem here that you've plugged into a 120 volt outlet, you don't want to talk about the voltage across just the resistor. You want to talk about the 120 volts. I mean, that's the number you've got at your fingertips. You know, it's a 120 volt outlet. So the voltage across the resistor is related to that 120 volts by this phasor diagram here. Hypotenuse times cosine gives you the adjacent side. So for the voltage across the resistor, you put in V cosine of phi. And so the point of this little story is that when it's AC current and voltage you're talking about, power is not just equal to I times V, like it is with direct current. It's I times V times the cosine of the phase angle, this phase angle here, for the circuit as a whole. The cosine factor is sometimes called the circuit's power factor. If you ever come across that phrase, that's what it means. Only the resistor actually consumes, well, ideally anyhow, under, you know, textbook conditions, only the resistor consumes energy. The resistor takes energy away from the flowing electrons, converts it into heat. The heat soaks away into the environment. Reactance does not dissipate energy like that. It very briefly stores energy in either electric or magnetic field, depending on whether you're talking about the capacitor or the inductor, and then it comes back into the circuit. Now, realistically, you can have some inductive losses under certain circumstances, but you know, under textbook conditions anyhow, ideally, all that happens in the capacitor is it takes some energy and stores it in its electric field, but then half a cycle later, when the electric field goes back to zero, the energy is returned to the circuit. Same thing with the coil. Energy is taken out of the circuit as the magnetic field builds up, but a half a cycle later, when the field goes away, the current goes back into the circuit. So, you know, talking about idealized circumstances anyhow, if you stick a capacitor or an inductor into an electrical outlet, it should not run up your electric bill any, because it doesn't use, averaged over an entire cycle, it doesn't use any energy. Only resistance does. Okay, resistance takes energy away and doesn't put it back. Of course, I'm not including here the possibility you might have some device like a motor in the circuit that takes energy out of the circuit in, you know, some other way. But find the power consumed in the previous example. Well, I'm not actually going to do this in the shortest, most efficient possible way. I mean, I'll tell you what the shortest, most efficient way is before we're done here, but I want to actually calculate the phase angle, so I'm going to do it with I times V times the cosine of phi. So maybe I'll just be honest right up front here. It's actually quickest to just use I squared times R, okay? In this particular question, we know the current because that was the answer to the previous question. And we know the resistance because it was given in the question, 300 ohms. And so I squared times R, bang, there's the answer. But an alternate approach, which would not be quite so unreasonable if you hadn't already done problem number 4, would be to calculate the power from I times the voltage times the cosine of the phase angle. Well, I know the voltage is 120 volts. Might as well write that down. And I know the current is, actually, I guess you have to have already done number 4 to do it this way also. But from number 4, I know that the current is 0.197. Anyhow, what it comes down to is I wanted to show you how to get the phase angle, and even if this is not the most efficient way of doing this particular problem, you have to sit there and listen to it because I'm in charge, and that's the end of the story. So we're going to get the phase angle from the phasor diagram. It's like before I made this video, I had to sit here for half an hour and watch some silly thing about how to prevent workplace violence, mandatory training for everybody in the college. I'm sitting here thinking, why do I have to worry about workplace violence when we're all isolated from the workplace right now? But I had to sit there and listen to that. So now it's your turn. Anyhow. Filling in, I mean, this is the general relationship. This is what it looks like on the formula sheet. Filling in the specific numbers that we have for this problem. For the resistance, that was the 300 ohms. XL minus XC, that was this up here, XL minus XC. So actually that's negative. So in this case, actually, the arrow would point downward rather than upward. It's a right triangle. Otherwise, you couldn't use a Pythagorean theorem. And, well, I might as well write this down too. In number 4, I determined that the impedance was 609 ohms. There's the thing I'm after, the phase angle. Now, since I know all 3 sides of the triangle, I could use any trig function to find phi, but I recommend avoiding using the cosine. I mean, in principle, the arc cosine of 300 over 609 would give you this. But if you do it that way, you're going to have to remember on your own that the angle is negative. You're going to have to, arc cosine of that divided by that is going to give you a positive number back on your calculator because, well, this turns out to be about 60 degrees. See, the cosine of negative 60 is equal to the cosine of positive 60, and it gives you the principal value. If you use the tangent, or for that matter, the sine, the minus sign is going to pop up there on your calculator, and it's harder to miss that way. So that's kind of the way I would look at it. I'm just in the habit of using the tangent because if you haven't gone to the trouble of figuring out the hypotenuse, that's the one you have to use because you know, if you start out knowing these 2 sides. Arctangent of opposite over adjacent, negative 530 over 300. That comes out negative 60.5 degrees. Once I know that, power equals, well, like I wrote up here, 0.197 times the 120 volts times the cosine negative. Now actually, because the cosine of positive 60 equals the cosine of negative 60, on this particular question, you'd get away with it. You know, if you forgot the minus sign, you're still going to get the right answer, which is 11.6 watts. But, you know, if the question is just simply what's the phase angle, which I think is exactly what you get asked for one or two of the homework problems, if you leave off the minus sign, that's going to be wrong. Resonance, which is the last part of the lab on this section. So you've got this RLC series circuit. Okay, I'm still talking about the same series circuit that I have been for the last 10 or 20 minutes. Let's say you've got one of our function generators from the lab. It's got a dial on it where you can dial up any frequency you want, anywhere from like 1 hertz to 1,000,000 hertz, or actually you can even go a little below 1. Not that there's any point to that. So if you were to measure the current flowing in this circuit as a function of the frequency, and for lab 12, the last part, you are going to draw a graph that you're going to draw this graph that you're looking at, you know, I'm sketching right now. We collect data by measuring the current at different frequencies, and when you plot up all those points, you get sort of a lump. A graph that looks kind of like that. This over here is actually an asymptote. The graph starts at 0, comes up to a peak, and then heading off towards infinity for the frequency, you've got an asymptote, but it eventually gets, you know, really small. So what's going on here is, like many things in life, it's like the story of Goldilocks and the 3 bears. This frequency is too small. This frequency is too big, but this frequency is just right. Low frequencies don't want to go through the capacitor, as I explained earlier. High frequencies don't want to go through the inductor. Somewhere in between, the reactances cancel each other out, and that is the resonant frequency. F for frequency, R subscript for resonant. Okay. Resonance occurs in other types of systems also, mechanical systems. Simplest example is just a kid on a swing, which is, you know, a pendulum. If you, well, you know, let me come back to that. Let me get the equation first. The current in this circuit will be largest when the number of ohms in the circuit is smallest. Okay, V equals I times Z. Z goes down, I goes up if you're keeping the volts constant. Now, as you change frequencies, here's the formula for impedance again. If you go turning the frequency knob, the resistance doesn't change. The resistor is just oblivious. It sits there like, what? Did you do something? It's, however many ohms that is, that's it. XL and XC, on the other hand, as I pointed out earlier, they both are functions of frequency. What's going to make the impedance smallest is if XL equals XC. Then this term here will go to 0, and the only impedance you'll have will be the resistance. Z will equal R at the frequency where these are equal. It's a really bad H. So this part of it is smallest when XL equals XC. XL is equal to omega L, and XC is 1 over omega C. And a couple lines of algebra. Multiply both sides by omega, multiply both sides by C, and then divide both sides by, I guess I could have just left the C where it was in the first place, actually. But divide both sides by LC, take the square root, and the resonant, again, the R here is not for resistance, R is for resonance, okay? The resonant angular frequency is 1 over the square root of LC, where maybe I should remind you one more time, omega is 2 pi f. Now, if you think back to, I think it was section 11, the last topic in section 11, if you have an LC circuit, this is the natural frequency that it vibrates with. In lab number 11, you've just got a coil and a capacitor and a voltage source and a switch. And when you close the switch, a pulse of voltage hits the circuit, kind of like a hammer hitting a bell, and the circuit rings for a little while after that. And this is the frequency that it vibrates with. Well, now we find that if you have driven oscillations, you have a source of alternating voltage that you apply to the thing, that this is the frequency that makes it resonate. And that this is true of resonance in general, whether it's a circuit like we're talking about now. I don't know where this pencil came from, by the way. It must be something left over from when the kids were little. I don't think I've ever actually bought a pencil since I was like 15 years. I don't know if I ever bought a wooden pencil. But anyhow, I like mechanical pencils better myself. Simple example, child on a swing. If you pull the swing back and let it go, let's say that it vibrates back and forth once every 2 seconds, just to make up a number for the sake of discussion. So that's the natural frequency of that pendulum. Now, the driving force is you pushing this little kid. Every time the swing comes back, you give a little push. Swing comes back where you are, push again. And without even thinking about it, the thing that any even half-rational person is going to do is make the frequency of your driving force equal to the frequency that the pendulum vibrates with. If the swing is going once every 2 seconds, you push once every 2 seconds. But just for the sake of argument, think about what happens if you drove it at almost any other randomly chosen frequency. Okay, the pendulum goes, the swing goes over, let's say you're over here. Let's say you decide to push it once every 2.1 seconds. Okay, so the swing comes over, and that's when you push on it. And it goes over, and it comes back, and then it's a 1/10 of a second in before you push it again. Well, okay, it goes over, and it comes back, and now it's 2/10 in before you push it. And then it's 3/10 in before you push it. And a few more strokes, and it's actually heading back towards you the next time you push it, which there are lots of reasons not to do that, one of which is you'll probably break your fingers. Another one is the little kid's going to get mad at you. But for purposes of our discussion here, the problem is that if you don't push it in the direction it's already going, then you're taking energy out. If it's coming toward you and you push it away from you, you're not adding to the energy in the swing. So you're taking it away, you're slowing the swing down. So if you just make up some random number and start pushing the swing at that frequency, it's extremely likely what's going to happen is the swing is just going to quiver around a little bit, okay? You put energy in for a few strokes, and then you take energy out for a few strokes, and then you put energy in for a few strokes, and you take energy out for a few strokes. But if you drive the swing at its natural frequency, which is once every 2 seconds, then you're always pushing it in the direction that the swing is already going, and it builds up a large amplitude after a while. This graph could just as easily be for the amplitude of the swing as a function of your pushing frequency. If you push it at its natural frequency, it's going to be going back and forth a nice big distance. At other frequencies, and for a swing, it would probably be a much narrower peak than I've drawn here, actually. Other frequencies, it's not really going to work very well. So this is the electrical counterpart. Well, I already showed earlier in this section how that it's the same differential equation that governs this kind of circuit. Or actually, that wasn't in this section. That was at the end of section 11 when I was talking about LC circuits. It's the same differential equation for a harmonic oscillator as for an LC circuit. And resonance is the same sort of thing also as it would be for a mechanical oscillator. What the word means in general is how that you get a large amplitude response if you drive it at the right frequency. If you drive it at some other frequency, you don't get nearly so much of a response, if any. And just like with a mechanical oscillator, that special frequency that makes the large response, the large amplitude vibration, that's the frequency of a free vibration. If you just let it vibrate without driving it, what's the frequency of that? Okay, so that's what resonance is. That's the resonant frequency for this type of circuit. Applications. Well, there's several applications where this kind of thing is used. Metal detectors is one, but one that I thought that I'd explain in a little bit of detail is the tuner in a radio. Now, a radio, and of course, when you say radio, it sounds like 1920s technology, but television is just radio where information for pictures is included along with information for sounds. A cell phone is basically just a two-way radio. It's kind of a glorified walkie-talkie. And so actually, well, for that matter, if you sit down with your laptop at a Wi-Fi hotspot, if your computer is communicating with the internet wirelessly. That's radio, okay? That's radio signals. So it's all an outgrowth of the original early 20th century technology that that brought you commercial radio in the early 1920s. Anyhow, the way it works is it's kind of like a transformer, in that, remember, in a transformer, you've got a primary coil and you've got a secondary coil, and they're arranged in a way so that the same magnetic flux passes through both of them. Therefore, a changing current in the primary circuit induces a voltage in the secondary circuit. And radio is the same basic principle as that, except instead of having the two coils a fraction of an inch apart, you have them miles apart. And in the primary circuit, the radio transmitter, you put a large amount of power into that. Commercial radio stations can be as much as 100,000 watts being applied to the transmitter. And the secondary circuit, which is in your receiver in your car or wherever you're listening to the radio, that's just a weak little millivolt kind of signal that's induced in there. It has to be amplified if you're going to drive a loudspeaker with it. But it's still the same principle, in that you've got a changing, well, to give the whole story, it's not just a changing magnetic field, it's a changing electromagnetic field. It's actually electromagnetic waves that are coming from the primary circuit. When that changing magnetic field gets to the secondary circuit, it induces a voltage in there that varies with the same pattern as the signal that was in the primary circuit. And if that's the pattern of somebody's voice, it can recreate the person's voice. But here's where the LC circuit comes in, or some people call it a tank circuit in a context like this. See, the thing is, there's more than one radio station. And as you go driving around, you don't want to listen to all of them at once. You don't want country music playing at the same time as heavy metal, playing at the same time as some guy talking about politics, playing at the same time as somebody else telling you what's a nice recipe that involves garlic and mushrooms, and you want just one radio station. So what you do, maybe I shouldn't have taken away my picture quite yet. After the signal has been induced on your antenna, you use a circuit similar to the one that I was just talking about here, and adjust its resonant frequency to the frequency of the radio station that you want to listen to. There are ways of making adjustable capacitors, variable capacitors. Like if I have, these two sheets of paper here, if these are two metal plates, and let's say I have the corner of them mounted on a metal rod like that, so that, and there's a knob on the end of this rod. When you turn the knob, it makes the one plate rotate like that, so that the farther you turn it, the less area there is in between the two plates. That will change. Actually, they have a whole bank of plates instead of just two of them, but that is how you can make a variable capacitor. Or you can make a variable inductor. You can have a long coil. There's a couple of ways of making a variable inductor. You can have a long coil, and one wire is attached to the one end, and the other end is on a contact, and you can just slide it along there. And this makes the inductance more, and you go the other way, it makes the inductance less. So either with a variable capacitor or a variable inductor, you have a way of changing the resonant frequency of this circuit, okay? Just like turning the tuning pegs on a guitar changes the resonant frequency of the strings when you want to tune the guitar. Oh, that string's a little flat. Pwang, pwang, pwang. You're picking on it, you know. I got to turn the tuning peg. Pwang, pwang, pwang. Now that sounds better. Adjusting the tension on the string changes the resonant frequency of that string. And in the same way that turning that peg on a guitar tunes the guitar string, turning that knob on your radio tunes this circuit so that it resonates at the frequency of the station that you want to listen to. And you see the next closest stations, you want to pick values for let's see. Oh, FedEx man just pulled up out front of the house. Anyhow, you want to pick values in your circuit so that you actually want to have a nice narrow peak, something that looks a lot more like that. And then you see the closest stations, aside from the one you want to hear, are there and there. So the station you want to listen to has a large amplitude, and all the others get filtered out enough that you can't hear them in the background. So anyhow, that's the story of how that's done. That's the background behind example number 6. So let's say that the inductance is just a little less than 8 microhenries, and the resistance doesn't have any effect on what the resonant frequency is. The resistance has an effect on how sharp the peak is. You know, is it a broad peak like this curve, or is it a sharp peak like that one? The so-called Q factor for that. If you're interested in learning more about this, you could look that up. I think it's in the textbook. If not, like everything else, it's on the internet. But anyhow, 1,000 kilohertz, right in the middle of the AM band. Apparently, you're more interested in some guy talking about politics than you are in music. If that's the inductor, what should you tune the capacitance to be in order to get that radio station? So this is just a quick little plug and chug kind of example. Section 12, number 6. One over the square root of LC. I'm waiting for the dog to start barking. Whenever the mailman or the FedEx man or somebody comes up on the porch, the dog always just goes berserk. Never once had a real burglar. I don't know why he's so paranoid. Just doing his job, I guess. Actually, that should have been implies, not equals. Solving it for C, which is what the question asked me for. Oh, no, that's an L. Okay, so I've done all the algebra. It's ready for me to just drop the numbers in. Well, 1,000 kilohertz is the same thing as 1 megahertz, 10 to the 6, in other words. Omega is 2 pi f, so the angular frequency would be 2 pi times 10 to the 6 if f is 1 times 10 to the 6. And the inductance is given in the question. Don't forget to take the reciprocal. Oh, speaking of forgetting things, I was looking at the answer going, wait a minute, these numbers I just wrote down won't give you that answer. Well, they will if you remember to square omega like you're supposed to. Okay. 3.18 times 10 to the negative 9th of a farad would be an appropriate capacitor. And the last topic in section 12 is transformers, which is something I've been talking about all along, ever since I started talking about Faraday's law, because transformers are a really good example of an application of Faraday's law. But I haven't said quite everything I wanted to say about them yet, and I left that for section 12 just simply because this is the chapter in the textbook where they've got transformers, is in the chapter on alternating currents. Primarily because you really need, as I think I already explained earlier, you need an alternating current. Well, I shouldn't say you have to have an alternating current for a transformer to work, but it's the most natural thing to be sticking into a transformer is an alternating current. They work the smoothest and easiest if it's AC. So here we have a typical geometry. You have the primary coil, which is the coil that you put electrical energy into. So for example, if this is the transformer in your cell phone charger, you have to step the voltage down to something like 5 or 6 volts, something appropriate to charge your battery with, and you're plugging it into a 120 volt household outlet. So this would be the 120 volt outlet that you're plugging the cell phone charger into. And the current goes through these primary windings and creates a magnetic field. The magnetic field lines follow the iron. Magnetic fields like iron. So remember, they're loops. Some of the magnetic field lines loop around like this. Some of the magnetic field lines loop around like that. But quite often the transformers you see in electrical devices are little square things like that. And that's the iron core for the magnetic field lines to follow that gives them that shape. So we're going to assume idealized conditions, sort of like frictionless surfaces when we were covering mechanics. We're going to assume resistanceless wire that this coil has been made out of. So therefore, there is no potential difference due to Ohm's law, because we're saying the resistance is small enough to ignore. The voltage across this coil is a self-induced voltage from Faraday's law. So I wrote down Faraday's law once for the primary coil. V1 is the voltage across the primary coil, equal to the number of turns in the primary coil times the rate that the flux through it is changing. Now, as I probably said, well, as I may have said several weeks ago, but it repeats here, in a properly designed transformer, the flux going through the primary coil also passes through the secondary coil. So I don't need a subscript on the flux. Phi1 equals Phi2. It's the same field lines pass through both coils. Apply Faraday's law to get the voltage across the secondary coil. Okay, so both voltages are induced voltages given by Faraday's law. Divide the one equation by the other to get the ratio of the voltages. Because this part is the same, it cancels out. And the moral of the story is that under ideal conditions, the ratio of the voltages is the same as the ratio of the number of loops. So if, for example, you're trying to take 120 volts and step it down to 6 volts, then this coil should have 20 times as many loops as this coil does, because if you got a 20 to 1, 6 volts times 20 gives you, I think I did that right, or is it 5 volts? That's what I get for trying to do math in my head. 120 divided by 6. Yeah, 20. I did that right. 20 to 1 ratio with the voltages, 20 to 1 ratio with the number of loops, okay? So maybe you've got, I don't know, 1,000 loops on this coil and you got 50 loops on that one or something like that. Going along with that, you've got conservation of energy. Under ideal conditions, the amount of energy per unit time, which that's what the word power means, being drawn out of these wires equals the amount of energy that's being put in through these wires. Now, realistically, a little bit of energy is lost to heat because of electrical resistance, and there can be eddy currents in the iron core that might cost you some energy. But, well, the nice thing about an introductory course is you can just shrug all that off and say, oh, that's small enough to ignore. So, of course, power is actually I times V times the cosine of the phase angle. But if you're operating it in a way that the phase angle is close to 1, so that the cosine factor doesn't complicate life, then I times V on the one coil would equal I times V for the other coil. So what this is telling you is that there's a trade-off because of conservation of energy, there's a trade-off between amps and volts. If you step the voltage down to 20 times lower, 120 volts here, 6 volts here, because of this, you will be stepping the current up at the same time. If you've got 1 amp in this circuit, you'd better have some heavier wire in this circuit because you're going to have 20 amps going through there, okay? Voltage goes down by a factor of 20, the current goes up by a factor of 20 to deliver the same power. So, one more example. This recording ran a little on the long side, but that's all right. Some of the other ones ran a little on the short side. We're not actually restricted to a 55-minute period here. I wanted to finish the section. So, an application where you'd want a significant amount of amps is to weld with, because, I squared R heating, you want to melt the metal. Plus, you want the voltage fairly low. So, to reduce the risk of electrocuting the person who's doing the welding. So, it says we've got 220 volts on the primary, and how many turns should, it gives 1,000 turns on the primary coil. If you want to have 200 amps in the secondary circuit, if you're designing this piece of equipment, how many loops should you be putting on the secondary coil? So the number of loops appears in this equation. Voltage across the secondary, voltage across. On the formula sheet and in the note packet here, I called it V2 and V1, and that's fine. You can do it that way. I was in the mood to use letters instead of numbers. S for secondary, P for primary. So solving that for the thing we're looking for, the number of turns in the secondary coil is the number of turns in the primary times the ratio of the voltages. So I know that and I know that, but I've got to figure this out before I'll get my answer. And that's where that other equation, the one about power, comes into it. The voltage across the primary coil times the number of amps in the primary coil equals the voltage across the secondary coil, number of amps that's there. That implies that my secondary voltage is the primary voltage times the ratio of the currents. Filling in the numbers. On the primary, we plugged it into a 220 volt outlet, and we've got 15 amps flowing at 220 volts. Well, one mistake with any problem that involves ratios like this is people getting the numbers mixed up with each other. Keep in mind what ought to be happening. When the voltage goes down, when the number of amps goes up, the voltage should be going down. There's a trade-off between the volts and the amps. So if 15 amps is going to get stepped up to 200 amps, then it should be that the voltage is being stepped down. And if you're getting the opposite kind of thing for the answer here, that means you've switched some of your numbers. Go and fix it. So 16.5 volts, which might be a little on the low side to weld with, but I mean, you got to have enough voltage to strike an arc with. But don't want too much higher than that, though. So now that I've got that number, I fill in my numbers here. 16.5 volts for the secondary and 220 volts for the primary. And the answer is, you want 75 loops in that secondary coil, and that'll make it do what you want it to do. Okay, that's the end of section 12, and not a moment too soon. The next page here is the review for the third exam. As I record this, you haven't taken the second exam yet, and I'm getting a little ahead of myself. But I'm going to just leave this for you to work with. The answers are in the, they're in the website. I've scanned my solution sheet for this, so if you don't get the answers that are shown here, you can go and look, or for that matter, if you do get the answers that are shown here, you might want to look at it and see if I did it a better way than you did. And shoot me any questions on that. And maybe I should put this. That's the end of today's presentation.